Hi, I'm Brandy Heflin. I'm a personalized physics instructor and I help high school and college students feel confident and successful in learning physics. One of the things I love most about physics is that it's the study of relationships between measurable physical quantities. So every important equation can be developed in the lab. This is a process called modeling. Our models include conceptual and mathematical relationships. I want to take a little time to break down some of the key aspects of creating those important equations from our lab data, which are our quantitative or algebraic representations within our models. Today, I want to discuss how to interpret slopes and intercepts of linear models, because those are the simplest models to recognize and use. You all probably remember slope-intercept form from algebra, good old y equals mx plus b. So let's talk about what the slope and intercepts of a linear model can tell us about a physical situation. For a linear graph, the slope, y-intercept, and x-intercept can yield valuable information about the physical situation. The slope tells you the amount the dependent variable changes in response to each equal size change in the independent variable. And the intercepts tell you the value one of the variables had when the other one was 0. So here's a simple example. Let's say you want to determine the relationship between the mass of an object, m, measured in kilograms, and its weight, w, in pounds. So this is relating two measurements from two different systems. So you can place masses of 1 kilogram each on a scale, going up to 4 kilograms total, and then you can record the scale reading and you could obtain the data seen here. When we plot the data from the table on the previous slide, we get this graph. Notice that the dots all lie on this nice straight line, so to get the slope, we can simply pick 2 points. And I'm going to take 0, 0, and 4, 8.82. So to get the slope, we will do rise divided by run, which is, of course, our change in our y-axis variable divided by the change in our x-axis variable. So our y value ends at 8.82 and it started at 0. And our x-axis variable ended at 4 and started at 0. So this gives us a value of the slope of 2.205. And if this were math class, you'd be done. But since it's physics and these values that data that we collected have units associated with them, things that we use to measure these variables, units that we used, we need to put some units on our slope as well. So our vertical axis variable units were pounds, and our horizontal axis variable units were kilograms, so 2.205 pounds per kilogram. So to interpret this, we could say every 1 kilogram increase in the mass of an object produces a change in increase specifically. We don't just want to say change, we'll want to say an increase of 2.205 pounds. So there we go. And so since both of these variables started at 0, when there's no mass, there's no weight that we can measure, we could say that this is actually the conversion factor between these two quantities. If you have a number of pounds, you can divide by 2.205 to get your number of kilograms. Or if you have a number of kilograms, you can multiply by 2.205 to get the weight in pounds. So let me note that for you, that this is a conversion factor. So here's another situation. Some students can hang a mass of 100 grams from a spring whose initial length is 5 centimeters. And then they add more masses of 100 grams each until they've hung 1,000 grams total. And with each new mass that they add, they measure the new length of the spring. So just note that the numbers in the diagram don't match up to the numbers given, but I wanted you to have a picture to represent what we're doing for this lab. Here's the data that these students collected. And notice that we talked about length in the problem setup, but stretch is what appears in our data table. Stretch in this case means the initial length of the spring, L sub I, subtracted from each new length, L sub F, where I means initial and F means final. So we could say that S equals LF minus LI. So when we plot the data from the previous slide on stretch versus mass, we get this graph. Conveniently, all of our data points lie on a straight line that's shown. To find the slope, I'm going to need to pick 2 points that are on the line. So I'm going to pick 100, 3 and 600, 4 because those give us a nice whole change of 1 centimeter on the top. So we'll find our slope with the change in the vertical axis variable divided by the change in the horizontal axis variable. So we have on top 4 minus 3 and on the bottom 600 minus 100. So that gives us 1 over 500. I'm going to pause here to talk about the units because I find interpreting this particular slope in this format a little bit easier than when we have the decimal. So our vertical variable units were centimeters and our horizontal variable units were grams. So let's interpret this. Every 500 grams of mass added we could say increases the stretch of the spring by 1 centimeter. So before I go talk about the decimal version, let's interpret this for a moment. If we had a different spring where we added the same masses and it stretched more than 1 centimeter for each 100 gram mass that we added, we could imagine that would be a much looser spring, more like a slinky than the little spring that you find inside a retractable pen. On the other hand, we might have yet another spring that stretches less than 1 centimeter for every 500 grams that we add. And so we can imagine that that's going to be a much stiffer kind of spring. So what we're seeing here is that our slope is telling us about the stretchiness of the spring. And of course, stretchiness is a highly technical term, of course. So let's go back to talking about the decimal form of this slope. If I go ahead and calculate that, I will get 0.002 centimeters per gram. And there's nothing wrong with interpreting this as every 1 gram of mass added increases the stretch of the spring by 0.002 centimeters. But it would be very strange in a physics lab to add only 100 grams of mass at once. And in a high school physics lab, we don't have the tools that could measure something in the thousandths of a centimeter. So leaving this as 1 centimeter per 500 grams is fine. And it's also okay to take the decimal form, but we might want to think about which one makes more sense to report when we want to interpret our slope. Let's go through one more example of interpreting slope. So in an experiment to determine if a car was slowing down steadily, the speed of the car was measured every 5 seconds, and here's the data that was collected. When we plot the speed and time data for the car on the previous slide, we get this graph. And notice what's different is that this graph has a negative slope. So our rise is actually a decrease in our vertical axis values. So let's pick two of them. We'll take the two at the ends, 0, 20 and 25, 0. And again, we will do change in our vertical axis variable divided by change in our horizontal axis variable. Our y-axis ended at 0 in value, but started at 20. And our run here, our x-axis values, ended at 25, but started at 0. So we get a decrease of 20 on top with an increase of 25 on the bottom, and that gives us negative 0.8. These units are going to look a little weird, but we do vertical axis variable units, miles per hour, divided by horizontal axis variable units per second. So this shows a decrease of 0.8 miles per hour for every second that the car runs. So let's note this here, that every 1 second increase in elapsed time produces a decrease of 0.8 miles per hour in the speed of the car. And this idea of the rate of change of the speed of a car is actually called acceleration. You'll learn there's a little bit more to it when you actually study this, but for right now, this is clear enough. So our slope tells us about the idea of acceleration. So we just looked at 3 different data sets, and we got 3 different meanings of the slopes. So we saw the slope of the line that best fits our data shows the conversion factor between kilograms and pounds, the stretchiness of a spring, and the acceleration of a car. And these all have in common the way we interpreted the slope. And I'm going to go ahead and write it out a little fancier than what we did on the slides. For every 1 independent variable units increase in our independent variable, the dependent variable increases or decreases by the slope value and then the dependent variable units. So for every 1 kilogram increase in mass of an object, its weight increases by 2.205 pounds. For every 1 gram increase in mass hanging from a spring, the stretch of the spring increases by 0.002 centimeters. For every 1 second increase in elapsed time, the speed of the car decreases by 0.8 miles per hour. So here's a format that you can use to help you interpret the slope of your linear data sets. Now let's talk about intercepts. Let's come back to that speed versus time graph because it was the first one that we had a clear y-intercept on. So our y-intercept is right here, and that value is 0, 20. So when the time elapsed was 0 seconds, the speed of the car was 20 miles per hour. In fact, let me write that for you. So our y-intercept here shows the value the dependent variable already had when the independent variable was 0. And in fact, this idea of at 0 seconds the car was moving 20 miles per hour is something called initial speed. For an example of what an x-intercept can tell us, let's consider a photoelectric tube. This is a device which emits electrons when it's hit by light. A photoelectric tube is critical for solar cells. And the more intense the light that shines on our photoelectric tube, the more electrons are emitted. So the light intensity I is measured in lumens, which is abbreviated lowercase l, lowercase m. And a sensitive meter measures the number of electrons emitted in millions. And we will use the abbreviation N for our number of electrons. And the following data were obtained for this experiment. So one thing that's different with this data set is that our points don't already lie on a nice straight line. So we have to apply something called a best fit line. And I used a spreadsheet program to do that. We can still, however, take a look at our intercept down here, and our value is 15 lumens of light intensity and 0 millions of electrons. So what this means is when we shined just a few lumens of light intensity on our photoelectric tube, nothing happened. And so we turned up the brightness a little bit, and we shone a few more, nothing happened. And then we shone even a little bit brighter light and nothing happened. And then finally, after we've reached 15 lumens of light intensity, we start to see some number of electrons emitted. So this intercept is telling us that the independent variable had to reach some value before our dependent variable changed. In this particular situation, we could call our intercept a threshold frequency, or sorry, a threshold light intensity. There's another variation of the photoelectric effect experiment where we deal with energy versus frequency. So I apologize for that slip. So we saw in these last couple of examples that interpreting the significance of one variable having a non-zero value while the other variable has a value of 0 reveals useful information about the system examined. In these two cases, we had the initial speed of the car and the threshold intensity of the photoelectric tube. Other systems will have different significances for their intercepts, and some will have both y and x intercepts that have meaning for the situation in question. I hope you found today's lesson on interpreting slopes and intercepts beneficial. If you would like to connect with me further, you can email me at brandyheflinphysics@gmail.com. You can check out more information about me and my services on my website, brandyheflin.com, as well as subscribe to my weekly newsletter. You can also visit virtualphysicsofficehours.com for more information about my office hours style tutoring program that is opening in September. And last but not least, you can find me on Facebook. I'm Physics Tutor Brandy. I'm Brandy Heflin. I love physics and I love helping you. Until next time.